We are stardust, or so they say. Long ago, giant exploding stars spread clouds of cosmic dust. Some of the dust coalesced into our solar system. Over time, on this planet, nature put it to use in an increasingly complex experiment called life. We've been using components of the dust cloud, iron, aluminum, and silicon, to look back out into space. What we've learned has only deepened the mystery of our place in the universe. Scientists and philosophers alike want to know, is life a fluke, a lucky roll of cosmic dice? Or is the universe somehow fine-tuned to allow life to arise and flourish throughout the cosmos? We are living in an age of precision cosmology, with new generations of giant telescopes on land and specialized instruments in space. Astronomers are probing the forces that shaped our universe. They are documenting its behavior on the largest of scales, going back to the first micro moments of its existence. They are charting its evolution hundreds of billions of years into the future. For all we have learned about the universe as a whole, profound questions remain. What does it all add up to? How do you explain this rise of complex life? Intelligent life. Some scientists point to the finely tuned interactions of gravity, electromagnetism, and the strong and weak nuclear forces within the atom. If the strength of any of these forces had varied only slightly, the universe might have flown apart and dissipated moments after it was born. Or gravity might have reined it in, forming one giant black hole. In either case, the universe would have no galaxies, stars, planets, or life. Was the basic layout of physical laws a coincidence? Or was it somehow meant to be? One answer from what's often known as the anthropic principle holds that the universe is uniquely suited to spawn life. To some, this implies that the universe is imbued with purpose. We, who are able to observe the universe and document its workings, are proof that this is so. But that conclusion, which can't be falsified, is more of a religious or philosophical concept than a scientific one. Consider the broad arc of cosmic history. Trillions upon trillions of years from now, all the stars in the universe will slowly burn out. Much of the matter we see in galaxies will gradually drift in toward their centers and be swallowed by black holes. All will go dark, eventually fading into the dark reaches of infinity. Overall, the evolution of life and intelligent life is a minor event, probably confined to a relatively narrow window of time. There's another way to ask the question: are the processes that give rise to life central to the way the universe works? In search of answers, we'll explore the origin of two of life's most important components: water and dust. Our story begins in the earliest moments of time, when the universe was awash in hydrogen gas. Gravity drew it into denser and denser regions, where the earliest stars were born. Generation after generation of stars formed and died. In the larger ones, fusion produced the elements carbon and oxygen. They became, by mass, the third and fourth most abundant elements in the universe. Heavier elements followed, including those created in the violent death of large stars. This animation depicts a supernova spotted by Chinese astronomers in the year 1054 AD. The star was utterly destroyed, except for a spinning ultra-dense core the size of a city, a neutron star, and an expanding cloud of gas and dust. Astronomers have been poring over the Crab Nebula, still growing at a rate of 1,000 kilometers a second. What they found is that the filaments of matter that roared out of the blast contain large volumes of dust, an array of mostly carbon or silicate compounds that absorb visible light. These solid particles are crucial for the formation of solar systems. Within the Crab Nebula, there is enough dust to make some 30 to 40,000 Earths. Over time, and after countless stellar explosions, dust has collected in dense pockets throughout our galaxy. But dust grains can be found throughout intergalactic space as well. Some might have come from the earliest supernovas. There is another source as well. Since the 1960s, astronomers have been studying bright beacons of light that shine from the centers of distant galaxies. A quasar's power source, they've found, is a black hole that has grown to millions, even billions of times the mass of our own sun. The thinking is that magnetic fields leap off a disk of matter that's spiraling into the black hole, drawn by its extreme gravity. These fields channel a portion of the inflowing matter out into powerful particle beams. The jet is part of a larger rush of matter away from the black hole. You can see it in a large spiral galaxy called NGC 3783, 30 million light-years from Earth. Astronomers use the Very Large Telescope Array in Chile's Atacama Desert to peer into the core of this galaxy, to study the environment of a supermassive black hole. From a disk of matter flowing into the black hole, intense radiation had created a dusty wind that is moving up and away from the black hole. The source of the dust is likely generations of giant stars that lived and died in the galaxy's central region. Black hole winds are now thought to have had a major impact on the universe at large. You can see it in a simulation of early cosmic evolution. It starts 12 million years after time zero and evolves within a volume 350 million light-years across. Not everything is known, including the nature of a dominant substance known as dark matter. Gravity draws matter into filaments, where it heats up, forming a vast luminous web. In time, tens of thousands of galaxies take shape. The action heats up where filaments meet. Giant bubbles of hot gas form and expand outward, pushing well beyond the central galaxies. This happens when galaxies merge, sending streams of matter into black holes that lie in their centers. These monsters, in turn, blast inflowing matter out in jets and winds. This seeds the wider universe with dust and gas. In our galaxy, dust has collected in star-forming regions, like the Orion Nebula, 1,500 light-years from Earth. At its heart is a star cluster called the trapezium, a brilliant formation first discovered by Galileo. It pumps out a wind of ultraviolet radiation that clears the surrounding region and makes the gas glow. In its midst, perhaps 1,000 hot young stars are being born. Some are blasting out jets of radiation that carve out ghostly red shapes in their surroundings. Around young stars like these, enshrouded in dust, nature sets the stage for the alchemy of life. Within these solar nebulae, gravity can build an array of bodies, from rocks to asteroids and planets. But the deck is stacked against it. As small objects merge into larger ones, they can collide with one another at high speed and smash into smaller pieces. If one does grow larger, friction with gas and dust can slow it down and send it spiraling toward the star. It takes a special set of circumstances to get the process going. Astronomers saw it with a millimeter wave telescope called ALMA. They used it to peer into the light of one newly formed star, 400 light-years from Earth. They found an odd feature within the ring of dust surrounding the star. It's a large vortex, perhaps created by a planet or a companion star circulating through the clouds. The region acts like a trap, holding the dust grains in place and allowing them to form larger objects. If planets can form, their dusty environment may play a more direct role in spawning life. Some 40,000 tons of dust and rocks rain down onto the Earth each year. Leftovers from the birth of the solar system 4 to 5 billion years ago. Interplanetary dust has long been known to carry organic or carbon compounds able to survive the journey through Earth's atmosphere. Scientists recently found something else on the dust particles themselves. Hydrogen ions, or protons, from the solar wind strike these particles. When these protons interact with oxygen in silicate mineral grains, they form H2O molecules, which then cling to the particles. This process was documented in lunar dust grains picked up by Apollo astronauts. It may be the source of water ice that is collected in the bottom of some lunar craters and is strewn about lunar landscapes. In addition to watery dust raining down onto the Earth, this may explain how comets and asteroids were able to generate stores of water and to bring them down to Earth. This process happens one grain at a time as solar particles race through clouds of dust or strafe the surface of solid bodies. It takes place in regions where stars are being born, where dust is prevalent and solar winds are fierce. That's only one source of water. Astronomers have spotted a protostar called L1448-MM, about 750 light-years from Earth. It is shooting matter out of its poles in high-speed jets containing oxygen and hydrogen. When these molecules reach a cooler environment, they combine to form water at a rate of 100 million times the flow of the Amazon River. To get an idea of how much water the universe makes, check out a quasar known as APM 08279 plus 5255. At 12 billion light-years away, it's one of the most luminous objects known in our universe. Astronomers were already amazed to find that it's spewing out large amounts of iron. Now they have found that its center is literally saturated in water, about 140 trillion times the amount of water found on Earth. Given that water is created and spread so readily, it's not surprising that it pervades our own solar system. At its edges, Pluto and its moon Charon are lined with a thick layer of frozen methane and water ice. The blue planets Neptune and Uranus get their color from the methane clouds that make up their frigid atmospheres. Within, charged particles circulate in a sea of liquid water, producing electrical currents and magnetic fields. Within the folds of Saturn's rings are countless particles of ice. Hovering just above them is the moon Enceladus, with an icy surface that makes it one of the brightest objects in the entire solar system. The Cassini spacecraft detected jets of water ice shooting out of its south pole. Scientists believe they are coming from an interior ocean, launched by the squeezing action of Saturn's gravity. The largest planet, Jupiter, harbors its own storehouse of water. The storms that drift along its surface are the result of water vapor rising and falling like thunderstorms. Beyond Jupiter's roiling atmosphere lies a water world, Jupiter's second moon, Europa. Its bright, smooth surface is crisscrossed by channels and grooves carved out by shifts in an ocean of liquid water or slushy ice that lies below. The faint emissions of water jets, illustrated here, were recently picked up by the Hubble Space Telescope. On our own moon, water ice is tucked into polar craters. There may well be additional stores in rocks below the surface. Mars, its surface etched by ancient dry riverbeds. If there's any water left, it too is most likely hidden below the surface. Then there's Venus. A thick carbon dioxide atmosphere has trapped enough solar energy to turn it into the hottest planet in the solar system. There's no water here. Earth, in contrast, is a water planet. Vast interconnected bodies of water, the oceans, cover 71% of its surface. Now scientists have detected whole oceans of water hidden in rocks deep inside the planet. The story of dust and water is central to understanding how life arose on this planet. As far as we know, these two components can be found throughout the galaxy. One recent estimate, based on data from the planet-finding Kepler Space Telescope, says our galaxy has around 8.8 billion stars with planets nearly the size of Earth, with surface temperatures conducive to the development of life. That means that in our galaxy, nature has had as many as 40 billion chances to get life started and evolve it from there. But with Earth as our only data point, we know that this process must survive a host of crushing threats. Planet-shattering impacts. Massive volcanic eruptions. Global ice ages. So is the presence of life in our universe a fact guided more by destiny or more by chance? We'll scan the heavens for evidence, a sign, or new ways to ask the question, what does it all add up to?